Okay. We're here. Well, we'll give others a few moments to join us. It's really free form until about 8:10. Okay, so just ask any questions you may have, anything that's working or not working, stuff like that. We'll start our real discussions after 8:10. Actually, I want to find out if anyone has if any of you have a tablet with a pencil that you can. No, nobody has an iPad with a pencil or an iPad.
I got one.
I have a drawing tablet too that I can plug into my
Hiram, right? Yeah. All right. So maybe today, at some point, you can take the screen because I had an idea in the shower today. Because two's complement, right? I mean, that's most of the time students find two's complement the most confusing off module 0, right? Even floating point is okay because once you understand that it's just scientific notation in a different way, floating point is very simple, isn't it? Because floating point is basically that number expressed as 2 parts, a times 10 to the n, right? So you express the a, which is an integer, and n, which is also an integer. So you have 2 integers, and you can represent any floating point number, any fractional number. So that's essentially what floating point is. So that's not so challenging to understand, right? So if you just spend a few minutes, you can know where the designers came from. But two's complement, that's the one that trips most of the students up. Most of the time, right? So I thought maybe what we can do today, especially since Alexandria asked a question last class, right, about two's complement and sign magnitude. I thought, okay, well, what we can do today is to take a bunch of numbers and then basically convert them side by side in a table, right, on an iPad or something. So someone pick up an iPad, and not now, okay? We'll give everybody 7 more minutes at least, right? So columns and numbers, and then translate them into regular numbers, what we want them to be, what sign magnitude would tell us it would be, and what two's complement, or some desired format, and then we'll see the motivation for two's complement, how it came about, right? I think that is the biggest roadblock to students, I think, is to understand the motivation, because any subject, not just computer science, I find that once you know the motivation, why someone did something a particular way, then you understand that you would have also done it the same way yourself, right? Then you don't have to remember that person XYZ or Pythagoras or Einstein or some person derived it this particular way, and I have to remember that, right? And that's harder. That's much harder than to understand why did they do that in the first place. What is the problem? What are they trying to solve, right? Once we understand what they're trying to solve, many students, I find, will automatically just come up with a book algorithm, right? So not even now, maybe 2B, right? Starting at 2B, there are some algorithms that you'll have to implement that won't make immediate sense, okay? I don't know. So some of you are, I think, enrolled in math classes, right? Math classes that are, I think even in high school, math starts introducing the concept of proofs, right? Proofs, yes, because in logic and math, you say this is this, right? How do you know that's true? How do you know? How do you know that how do you know that something I say is true, right? So you test it out. That's empirical testing, like in science. Empirical testing is you basically test it out in the real world, allowing for some error or the extremely unlikely case that something doesn't happen as expected, right? So that's empirical testing. So you can test it out. The other kind of testing is just logical testing, where you basically work out the sequence of steps starting from some absolute truth, right? You take something for granted and then derive things from there. And then right? Since every step of the way is necessarily derived from the previous step, right? If this is true, that has also got to be true, right? So that is an absolute truth that you have derived, which is not immediately obvious. So that is something that we get to prove a lot, right? A lot, repeatedly in math. How many of you can have that experience. I mean, you've done high school math, right? You're going to be doing math anyway, right? If you're in a computer science course, you got to be doing math on the side, not on the side, as part of the core curriculum, you got to be doing math. And so it's all about proofs. And so maybe some of you recognize that, where was I going with that? Yeah, recognize that some things are not obviously true, right? Some things are not obviously true, right? So we started with this truth and then derived A and B, right? And which have both got to be true, but they don't seem to be obviously true, right? So, and so in your exam, you would get a question, right? Say, I prove that, X, Y, Z equals IJK or something like that. And it's not obvious, but you can derive it step by step. And just like that, very similar to that, there are algorithms that you will have to implement. Okay, so for example, someone might have a problem and say, well, I have to control these drones, right? It's drones that my robot is driving in a particular pattern. For this particular application, they need to fly in that particular pattern, and I need to control it for these stimuli in a certain way. Some kind of, and that, well, if I were to do it manually, there's no hope because it's very complex. And I can't figure it out. And I can't even tell if there's one way to do it or many ways to do it. Or if someone told me that this is the way to do it, I don't know if that is right or not. Maybe I issue the instructions to the drone via my program, but it doesn't do what it's supposed to do. It actually does something else. Yes? We're talking about drones, but you have this experience with ordinary programs too, right? It doesn't have to be drones, right? As ordinary programs you write, they're supposed to do something, right? So you start off with a problem that's given to you on a spec sheet. Right. By the way, you have to switch on your camera, guys. Okay. I don't want to be talking to a blank screen. Okay. With just names on it. And furthermore, on a video, I checked on YouTube, even the names don't show up. Right. It just shows a blank, a generic avatar picture of, cartoon or something like that. So don't yeah. Then it's much more lively, right? Because then people can talk to you. Right. So let's say, Zaid wants to say something. He'll basically say, hey, Haram, you said that, and so on and so forth. It's much better when people look at our faces when we talk, I think. All right, good. And everybody else too, right? If you can, right? If you cannot, you have to be extremely extra vocal here in class and speaking up, interrupting me, right? Interrupting me is fine. Okay. And you should do it. You say, hey, stop there. Can you repeat that? Or, what you said was wrong. I am going to say lots of wrong things. Obviously, right? Everybody says lots of wrong things. So I am going to say lots of wrong things. And sometimes I will actually knowingly say wrong things just to make sure that someone has the opportunity to butt in and say, hey, you're wrong. Because that's the only way I can tell that if you guys are awake or not, right? Some of you basically switch on your, don't switch on your cameras and, with your names, you could just take off, right? So I got to say something wrong from time to time. So, and I don't, the thing is, even if that wasn't the motive to tell you wrong things, for me, it works out because, I get a signal saying, hey, that was wrong. And I know you're listening. That's not the reason why I started saying wrong things, because I've been saying wrong things in this class for a long time, right? Go back to lectures from several quarters ago. You'll see that I've said wrong things in lectures. And I've also told students that I'm going to be telling you both right and wrong things. Right. And the reason for that is that if you only told people right things, then they'll just believe you. Right. And after a while, and they'll say, yeah, it's true because, Anand said that in class. And that is like total nonsense, right? Are you going to live your life like that? Saying that time when I did a class at Foothill, right? No. So the whole idea behind teaching in any college, any university, right? Any institution of higher learning is not to impart information to you, right? Not to impart knowledge, but rather to use information. I don't know if people actually, or if teachers do it this way, but this is the way I think it should be done, teaching, right? So anyway, right? Teachers basically use information as examples to train the process of thinking of a student to be able to find the truth themselves without the teacher's involvement at some point, okay? Or we hope, right? We hope that at the end of 4 years, we can basically set you free. And then any problem you have, right? You can basically not have to ask anyone, right? How do you do this? How do you do this? Because it's just like a diamond, right? Everybody, when you're born, it's basically a diamond, but it's a diamond in the rough. You know, you can't tell it's a diamond, but it's there. And during the process of learning, what happens is that it gets, you know, pieces of it get chipped off, right? It's shaped up. And and the cut is painful. Many times it's painful. Every cut is a painful cut. And I think, drawing a rough analogy, people should not identify themselves with the piece that is cut and thrown away, right? Because, you know, it's painful because the diamond is going to suffer more cuts, but the cut is not going to suffer more cuts. It's basically cut and thrown away, right? So if you're afraid of those cuts, you're going to say, I'm not the diamond anymore. There's a lot of cuts coming in, right? Before the diamond starts sparkling like a real stone, right? Before everybody wants to have it. So, but it has to have a lot of cuts before, you know, lots of facets of your personality, right? But lots of things about you, about your true nature, they're covered up. Nobody can see them. Only you can see them, right? You don't show them to anyone. You're afraid because if you actually showed that true facet of your personality, people might find it ugly or people might say that's wrong, right? But at some point you realize, no, that's actually really beautiful. And people who think that's not beautiful, they're the ugly ones, really, because they can't see the truth, because they can't see what is really formed, what has internal consistency, right? So, and a lot of people can't see that, and they will, and so they can't recognize real beauty. And the unfortunate side effect is that when children at a very formative age are affected by such people, they will also not learn to identify what is real beauty, right? And they'll go after false things, you know, things that give false fulfillment. Eventually they'll shatter and you won't be left with anything because you identified with the cut and not the diamond. So I think what we need to do really is to, how did I start talking about this?
Can I ask a question?
Absolutely. Who's
it? Hi, so
Lee,
I was just confused on the participation aspect of the class. So you can earn participation points from lectures or Reddit. Is that true?
If you're in lectures and you're attentive and basically, you know, asking the odd question from every now and then or helping other people out, fine, okay. Even if I don't see you on Reddit, you know, ideally, I want to see everybody on Reddit. I want to see, because in the lectures, you're on a YouTube video and you say something brilliant, who in the future might actually, I don't know, maybe Google will have technology which will basically mine all of the YouTube videos out there, extract the text, right? It's easy, right? They're closed captioning all the text, all the videos right now. So it's very straightforward to do. Right. So they might actually index that and say, well, you know, this is a really brilliant piece of insight here. Who said that? How? Right. So now you can Google it and you find some web page where some brilliant student somewhere posted it on a blog. OK, but if it's on a video, nobody can tell. Maybe in the future they can. Right. And say, hey, Lebian said this incredibly cool thing in a lecture, but it was on video voice. Right. So participate on Reddit. If you're participative here, and you know, it's fine, because you know, at the end of the day, well, let's say at the end of the quarter, very, very likely, extremely slim chance that I will not remember you, right? In fact, you know, 5 quarters ago, if a random student turned up here, chances are, you know, over 75%, I would remember that name, the face. I would call out experiences we had on screen. So I remember, right, these things. So when it comes to participation grades, I don't go, what I described in the syllabus is basically just a rough guide because it's very subjective. I will, every time I'll see, right? So, oh, this, you know, Lebian, right, okay. Well, he was very participative, he helpful and asked a lot of interesting questions. Yeah, okay, 15, right? Okay, like that. But if, you know, many times what I see is people who I don't recognize at all, right? They have been absent in lectures. I don't see their face, so I can't tell. So that's why, you know, that's the important reason to see your faces is because then it is better for me to attach, right? And then into my memory. And then when it comes time to grading, if it's something that someone I absolutely don't recognize, then I go to Reddit, do the search, right? I have to go to Reddit physically and search and see one or two posts the students have made. Oh, that's the other thing, now that everybody, most of you are.
So could I, can I explain 3 scenarios and like see if that would qualify me for participation points? So if I only came to class but never posted on Reddit, could I earn full participation that way?
I would suggest that just to be, unless you're like, that's fine. If you cannot post on Reddit, but I would say post on Reddit.
What about the other way? If I only post on Reddit and never come to class, would that also qualify?
Yeah, but then that means you have to be like super duper, on Reddit, right? You can see some of the posts on Reddit. They're like extremely detailed. Some of the students, right, in the past, and I think it's harder to come up with these posts, rather than to come up in class and just be participative.
Okay, all right, thank you.
Yeah, and also if you have your camera on, the other advantage is you won't fall asleep. Yeah, okay, because without your camera, you could also fall asleep, given it's early in the day and all. So, so where I was going with that other thing is that I've noticed someone posted on Reddit just a few days ago, or maybe in 2B, right? I'm going to make an announcement on Canvas, okay? At the end of the quarter, I actually do get email from some students who say, hey, Anand, I did a great job on all of the exams, as you can see, right? And I aced all of the quests. I maxed out, right? And I still only got a B+. Why didn't I get an A, right? And the reason, and I say in the past, I've actually said, right? The reason is because it says in the syllabus you have to participate, but you never participated. I don't see a single post from you. And I say, no, I participated. I participated on our Discord channel and Slack channel. Do you guys have Discord and Slack channels for CS2A? Yeah, okay. So they say I participated there. I helped a lot of people out. You can go and check it out, right? But unfortunately, that doesn't work, okay? Nothing outside of Reddit counts. So you can be the world's most helpful person, Mahatma Gandhi, and on Reddit, not on Discord, but that's great. You earn a lot of gratitude from other students, but you won't get any participation points because we've got to be, so that's one thing. And the other thing also is the other people have not read the syllabus, I think, because some students have Reddit handles that totally don't match, right? So like, for example, Jared, not you, right? I don't know what handle you have. I'm using your name as an example, right? Instead of Jared Cruz, maybe use Jake Cruz, that's fine, or Jared C, that's fine, or, right? But, so suppose he used a Reddit handle, like, JC or Jesus Christ or something like that, right? So absolutely no relation to, I can't tell. How can I tell? Because there are people from outside, not outside of Foothill. They're questing too, and they're using crazy handles. So I can go and tell them, you got to use this handle, right? So the only thing I do is that, if it matches, that it has to match that pattern. It's a regular expression. If you know Unix, or right, if it has to match that pattern, if it matches that pattern, you get participation points. If not, then it's really hard, right? You may not even know why you got a B+. All right. So, and anyway, to complete that circle, the goal of teaching is basically not to give information, but is to train the person to tell, to train the raiser to train the good sense, right? To train the good sense, because everybody has good sense, but it just needs to be trained. Some positive examples, lots of positive examples, lots of negative examples, and also you being able to tell. Because what is teaching if you don't have any tests, right? If I just keep on giving you information, but I don't test you, right? Then you don't know. So all of those things are important. And that is why in my class, you have to not just be in the mode of absorbing information, you have to be in the mode of examining information all the time, because you never know. I can guarantee you can never know if what I say is true or false. Many times I will actually tell you false things, right? So the only way you can tell is by exercising good judgment and good sense. So basically just use it as practice, right? Many times, maybe 100 times before the course is over, right? You'll have a chance to think about it. Not during the lecture, maybe, right? Maybe when you're biking home or something like that. Maybe you'll be thinking, hey, Anand said that in class. Is that really true? Does it make sense? but that's the way to find out. Not by saying, well, is it true? Let me ask my dad. Let me ask my mom. Let me ask someone else to find out if it's true or not. That's not the right way, right? The right way is, if you can't find out if it's true or not, leave it out there in a tentative state, right? Don't make up your mind based on an answer someone else gives you. Just leave it out there. Unless it's a life or death situation, leave it out there and you'll eventually find the answer, right? Yourself. Then it's your own answer, not someone else's answer. All right. Wow, it's 8:21 now. I think we can start. Who was it that had an iPad and was willing to go? I think Hiram, you were willing to go, right?
Yeah.
Yeah.
Sure.
Anytime you like, you can take the screen. But before then, let me make sure. Does anybody have any questions? Anybody want to any particular topics that are confusing? You need us to dive deeper into today. We can do all that, right? Today is the last lecture of data representation. Next class onwards, we won't have to share the iPad unless absolutely necessary. We'll just go with sharing screens. So you got to be, you got to have a computer, and you need to be able to share your screen. Hopefully, everyone will get a chance, right? And by the way, participation, Lei, you asked that question. Everybody needs to get at least one chance to go and code live on screen, okay? It's a very unique opportunity. You don't get it in other classes. Well, you do get it in some classes, right? But it's not a given. Not everybody gets a chance, right? So take advantage of this. And in this class, every one of you can and should get a chance to grab the screen and share your screen with the rest of us, and we will be coding a problem, and you will be typing it in, and I or someone else will basically call out the code if you're stuck, right? Or we can just call out the code, doesn't matter. You can look at the past videos to see what I mean. But sometimes people just, some of the students will basically just keep typing. Even while I'm saying this is the next statement, this is what we got to type, they've already typed it out. So all of those fun things can happen. All right. So let's take a
quick question.
Yeah, sure.
So are you gonna walk us through how to download the portal and everything, so we can start coding C++, or is that on the syllabus? Do we have to work through it in the syllabus?
Well, you don't have to work through the syllabus, but you have to read the syllabus and understand it. In order to compile your C++ programs, I don't know, someone else, Agnes said she was using Visual Code, Visual Studio. Did you say you were using you
yep.
asked, right?
I'm using VS Code and just typing in the G++ command on my terminal to compile.
Right. Yeah, that's right. Because Lei asked, was that you? Lei asked you a question on Reddit?
Yeah, I think so. On Reddit?
Yeah. Anyway, so yeah, VS Code would be a good option. If you have a Mac, just use Xcode. Right? Because it's a compiler, they're all pretty much the same. Why install a brand new one, right? Unless you plan to be switching environments and just need to be comfortable with, one IDE, then VS Code is good. Then regardless of whether you're in Windows or you get the same experience, yes? But if you're primarily a Mac person, I find Xcode is good enough for most purposes. Okay, does it answer your question? Zaid, okay, good. Zaid, was that you? You were
yeah,
talking?
that was me.
I think you need to adjust your camera because only the top of your head is visible. Okay, great, thank you. All right. Any other questions? Otherwise, we can just get started. Here's what I was thinking this morning. Okay, let's write down the numbers. So all right. So before we even share the screen, someone answer this question. Okay, how many different okay, all right. So look at a square. Okay, a square. Square has 4 lines. Yes or no? So that's 4 lines. Okay. Now imagine you can take one of those lines away. You get a different shape. Yes. You get a C, right? You take this one out, you get a different. So imagine you can take either one line out, or 2 lines out, or 3 lines out, or 4 lines out. Okay. So we want to say how many possible different shapes can you get out of a square if you had the freedom to erase one or more lines? How about that? Is that an interesting question to think about now? Because it's going to lead directly into what we're going to do, right? Some of you probably already know where we're going with this, but don't think about where we're going with this, right? Just try and solve this problem, right? You can use a piece of paper and pencil if you want, okay? And see. So you have a square, and you know what? I didn't have the square idea in the shower. You know, I had the idea of what we need to do, but this square idea just came up, and I think it's really cool. So what we need to do is just basically have a square, and then you want to say you can rub off one or more lines. So obviously one shape is where you don't have any lines at all. That's a valid shape too, yes, because 0 is a number in the same way, right? Or, you know, so in India, we say silence is also a sound, right? This is just like 0 is a number, a quantity. 0 is a quantity. Silence is also a sound, right? It is a sound which you can't hear. So just like that, you know, blank, nothing at all is also a shape. It's a non-existent shape, but it's a shape, right? So that is a shape. So count that as one of the shapes.
Anand, does the placement of the lines matter?
Hmm?
Does the placement of the lines matter?
Yeah. It has to be, you know, square, right? It's a square.
No, as in like, if you have the same shape, but you rotate it, is that a different shape or the same shape?
No, all right. So let's say this, can you see? Yeah, okay. So you have this, right? But you're saying if you rotate that.
Yeah, is that a different shape?
No, it's a different shape, right? Because this is missing, not this. Yeah. So so think about, and so how many possible different shapes can you get? So the very first one already we know it's blank. All 4 lines are erased. That's the very first one, right? Let me form the first shape after that, right? So let's say that's the second shape. The second shape is going to be when, you know, the leftmost edge is visible, right? The third shape, that one. And the fourth shape, that one, right? And you can keep, you know, fifth shape maybe is a full square. The sixth shape is, you know, that one with this one gone. Sometimes you can come up with a systematic way of deriving this. Yes? Okay. All right. Now, you don't have to go through this process, and we don't have to, but we just need to know that there exists a systematic way in which you can enumerate all of the shapes. Yes or no? Okay, good. Now, all right, well, one little step before we go into the sharing of the iPad, Hiram. How many possible shapes are there? You don't have to enumerate each one. How many possible shapes can you make like that? Bam, 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 right? Erasing one or more of those lines. How many possible shapes can you make?
Would it be the combinations of 4? So 4 factorial, 24?
Actually, it's not factorial because, you know, it's not factorial. You're getting close. You do want that, but in fact, you know what? Let's share the screen right now. And you know, in fact, what we'll do is by the time we're done with this, you'll know the answer to this, right? So let's you know, open the screen, share your screen, Hiram, and then your iPad. I think what you need to do is run Zoom on your iPad. And then join the meeting through Zoom. And
no. It's not a problem. So a drawing tablet is like this. It just plugs into your computer and you can use it as a mouse.
Oh, cool. Okay. Is it
fancy?
Allow you to share that? Does
yeah.
allow you to share that? Okay, cool.
Yeah, I'll just share my notepad. I can. Yeah. Okay. Can you see that?
Great. Yeah.
Okay.
Great. Yeah. Wow, you've even got a title and everything. So this drawing tablet is pretty cool. Okay. All right. Okay. So let's undo that. In fact, what we do is just draw a square. Just draw a square with 4 lines. All right. Great. Okay. Now, here's the leftmost line, right? So the left. So now erase the 3 lines and keep just the leftmost line. All right, now that's one of the shapes. Now, just with the leftmost line, I can have 2 possible shapes, yes or no? With the leftmost line present and the leftmost line absent. This, regardless of all the other ones, regardless of all of the other shapes, right? Regardless of the other 3 lines in this faces, edges of the, not edges, edges of the square, just this one line, this one edge tells me that I can have 2 variations. I can have a variation in which I'm present and a variation in which I'm absent. Yes or no?
Yeah.
So basically there's 2 families of your shapes. One family of shapes has that present. The other family of shapes has that absent. Yes or no? Okay, all right, good, good, good. Now, how can you make those two families identical? Right? In fact, the two families are identical except for the fact that this guy, this one guy is, present here and absent there. Yes? So you can make the two identical by just removing this guy from one. Then there are two. So the only thing we need to understand here is that except for that line, the two families are identical. Yes or no? Okay, great, great. Okay. So now consider one more line, right? And you erase that, and then you have consider another edge. You can make exactly the same argument for that too. Yes or no? All right. So each person can say that with me you have this, and without me you have something completely different, right? So each person gives you two possible universes. And you have four such people in the square, 4 lines, and each line can split into 2. So how many times can you split into 2 if you use all 4 lines?
8 times or 4 times, which is 8 different.
You're getting close, Joshua.
Yeah.
You're getting
yeah.
close.
You can split 4 times, which is 8.
Okay, well, I think you have the right answer, but basically you started at you started at 0. But if you start at 2 to the 0, which is actually 1, right? Because with nothing at all, you have 1, right? You add 1, you get 2. You add 1 more, you get 2 to the 2, which is 4. You add 1 more, you get 8. But we add 1 more, you get 8 double, 16. So each line basically tells you, I can give you 2 versions of it. Whatever you have so far, I can give you 2 versions. Each line tells you, so far, whatever you have, I can give you 2 versions of it. One in which I'm there and one in which I'm not there, right? So the next line comes in and doubles it again. So each line doubles it 1 time. Yes? So this is basically the absolute fundamental, right? So once you're solid with this, I think, the rest of computer science basically follows. It's like a dominoes, right? So this is the bit that you may need to spend a little bit of time really ingraining into our heads. But it's really solid to understand this is how the counting actually works, right? Every bit basically doubles our space of possible representations. Every bit you add basically doubles. Okay, now let's split up the square. Let's split up the, so instead of writing the square like this, right? You drew the square like this, bam, 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 bam. Let's just split it up and take the edges and write them side by side, right? Instead of drawing them like this, we're gonna draw them like this, bam, 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 bam. The 4 sides of the square are just gonna be our 4 lines. Can you do that? Can you, Hiram? Can you, yeah, so the second line is horizontal. That can also be vertical. There are no, just all of them vertical. Make them all vertical lines, yeah. Make them all vertical lines. So you have 4 ones, basically 4 ones, yes? Yeah, actually erase that and say 4 ones. Erase that and say 4, 1, 1, 1, 1.
4 ones.
Yeah, erase the whole screen and say 1, 1, 1, 1.
Okay.
Yeah. In fact, it'll be easier if you just write a vertical bar instead of
Okay.
the artistic one, because it'll be, because we're going to be having to do a lot of these, right? Okay.
Yeah.
So does everybody now relate to what we did with squares? Every one of those lines is a side of the square. Yes or no?
Looks like it.
Okay, good. All right. So we just need to, so what we're doing here is the square is still there, but we rotated our brains, right? So the wall is there, but we rotate our brains, we can look at it in a different way. So that's basically what's happened here. All right. So now each of those lines is saying I can either be present or absent. Yes. So essentially what we have there is 4 places in which you can have 2 shapes, a vertical line and a non-existent vertical line. But a non-existent vertical line is hard to see. So let's just replace a non-existent vertical line by something else. Maybe a smoosh, a smudge or something. We'll actually use a circle, right? Saying that there's nothing. All right. So what we'll do, therefore, is draw 4, fill in the blanks underlines, right? For 4 fill in the blanks underlines somewhere, because we're just now going to do a pattern. of, one under the other of all possibilities, right? So erase everything, and let's write the very first pattern, right? We're going to do many of those. So right at the top, four of our shapes, which is going to be 0, 0, 0, 0. Okay, this is the same as blank, 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 blank. Yeah, is everybody on the same page? Okay, that is our very first shape. Now we want to figure out how many possible shapes are there. There's 16 possible shapes. Yes, 16 possible shapes. All right, so the first shape is going to be these three edges don't show, but the last one, this edge will show. So we're going to say 0, 0, 0, 1, right? And then our system is basically going to be, the next one is going to be, we're going to be doing the exactly same thing as we do in decimal, right? When we count, what do we do? 1, and then 2, 3, 4, 5, 6, 7, 8, 9. But after 9, what we do is, we go back to 0, but the next one goes to 1. Yes, but here we only have 2, right? The line can either be 1 or 0. This is binary digits. It's, it's bits, right? So, so we have 1, but that's the last digit already. So how do you get the next one? So that 1 will turn into a 0, and the 0 next to the left of the 1 will become a 1. So that will be 0, 0, 1, 0. Yeah. Okay. So a lot of people. So that is the running joke in the Silicon Valley community, is that people think it's 10, but it's only 2 for computer scientists, right? So all right. So the next one is going to be 0, 0, 1, 1. Okay, now you'll see that it just keeps on repeating. Just do it. Everybody should be doing it, right? Not just Hiram, right? Hiram is doing it on screen for our benefit, but everybody should be doing it on a piece of paper, because once you do it yourself, you'll see the pattern. Because when Hiram is doing it and I say, or Hiram says, okay, well, I see a pattern here, and then you realize, yeah, there's a pattern. Now that you'll appreciate it for maybe 2 or 3 days, right? After that, it won't be a pattern to you anymore. Right? But if you do it on a piece of paper yourself, it'll be a pattern to you forever, for the rest of your life. Okay, so so that's basically what he's doing. So you should also do it on a piece of paper, right? It shouldn't take you a great deal of time. So essentially, those are all of the patterns. Those are all the shapes. Now you can answer that question that you had. How many squares can you get? You can basically take each one of those and assemble it into a square. Right? Because you can give names, right? You can say that this one is a left edge, that one's a top edge, there's a bottom edge, there's a right edge, right? So those symbols tell you which one is on and which one is off. So if you had to construct an LED display, for example, right? LED display. So you've seen all those digits in LED displays, how they change shapes and change numbers. That's how they do it, right? If it's a 0, it doesn't show. If it's a 1, it shows, right? And exactly the same thing happens with pixels on your screen too, right? So, except with colors, it gets slightly more complicated, but not much more. All right, so yeah, 2 to the 4, 16. All right, so is everybody okay with that? Okay, now Hiram, if what we'll do now is it possible to fit in all of those 16 patterns in one column somewhere? Maybe on the
yeah, I can just restructure this really quick.
Hey, leave that there. Maybe on the right. Yeah. Oh, you can actually do that?
Yeah.
Oh, but you lost the bottom one, I think. Oh, I see. All right, cool. So you got a 21st century tablet. Okay, all right. I was thinking of the other ones that started with W. All right, good. All right, so let's number them in decimal, like we know, right? On the right, let's just say the first one is 0. Not on the right, just after a tab or something, right? Yeah, like that. Where you wrote, right? Yeah, 0, and then 1. And then every third or fourth number, draw a horizontal line to link it up so that we can still sync up. Yeah, draw a horizontal line between the 4 and the numbers. Yeah, there you go. Cool. Is everybody okay with this so far? You know what I'm going to do? I can only see like 4 or 5 of you right now, so I'm going to reduce the size of Hiram's screen so I can see more of you. I can still read what he's writing. So, wow, you know what? The display on the screen is so sharp that Hiram's display is no bigger than a couple of inches. on the horizontal side, 1 inch and 2 inches here and 1 inch here, and I can read everything on that screen. So the display is so sharp. And I can see most of you here on that's great. Okay, all right. So is everybody okay so far? Saying that these are the 16 possible horizontal shapes, the 16 possible shapes we can get, 16 possible bit patterns. Bit patterns you can get with 4 bits. With 4 bits, these are the 16 possible bit patterns. Yes or no?
Yep.
Great, great, thank you. Actually, thumbs up is great, okay? Even if you don't speak up, a thumbs up like Alexandria or, Feng Feng, did you raise your thumb right now? Oh, I see, so yeah, you did. So I was just imagining, right? Okay, all right, good. All right, now let's say, for argument's sake, okay? So we're gonna touch on a lot of topics here, which is really cool. I like it, okay? Let's say for argument's sake that, the leftmost column is now binary. It's binary. It's using only zeros and ones. Yes? Okay. The second column after that is decimal, right? Because we're using, decimal numbers that we're used to, 1 to 16 and so on and so forth, right? Now, suppose we didn't have decimal. And we said, at the decimal after 9, it needs to go to 10 and uses 2 digits. That's really ugly. I want a system in which I'm still able to use only one symbol. Right? For each of those 16 shapes, I want to use only one symbol, right? And for the 17th shape, that's okay. I can go to 2 symbols there, but at least for the first 16 symbols, I need to use only one symbol, right? So how can we do that? So one way is to say, right, 0 to 9, a decimal just works. It's just one symbol, right? So on the right of the decimal, just create one more column and just copy 0 to 9 because we can still use that. The problem only starts with 10, right? 10 onwards, we are using 2 symbols. So, right? So now we want to say, well, we want different symbols now because we don't want 2 digits. We want to use. So one way to do that is to create special symbols saying, I got a 10, but it's not really a 10. It's a different symbol. I'm going to connect the 1 and 2, right? So it looks like this. It looks like that, right? So it's connected. It's not like a 10. So you say, I have different symbols now, but they, that's what they mean. That means 10, that means 11, 12, and so on. That's kind of ugly, right? So another way to do it is I just use letters from the English alphabet. So you can say A, B, C, D, E, F, right? Now I have 16 possible symbols, right? And each of those is a distinct binary number and a distinct decimal number. Yes? Okay, and this is all, this is basically a number system. You can use it just like any other number system. You can experiment on your own and find out, right? Or you discuss in the Reddit, it'll be cool. And like this, you can do, if you can actually go all the way to 25, 26 symbols, which is what module 0 has to do, right? Your name in English could be a number, right? Because each one of those could be a bit pattern, yes? From 0 to 26. So that's all right. Now, so we know how to represent these numbers. Now, let's say we want to do negative numbers, okay? Now let's look at what, Alexandria said last time, right? So let's say if we want to use sign magnitude notation, right? The sign magnitude notation. So 0 would be 0, all the way up to 9, everything is fine, yes? All the way up to 9, everything is fine, isn't it? Yeah, so let's just say, we'll say 0, 0, 0, 0 on the right. Right decimal. Was it decimal? No, that's hex. Yeah, hex. Thank you. Yeah, now the font size is starting to matter. Okay. All right. Okay, hex. To the right of that, you can say sign magnitude, right? Say SM. No. Actually, all right. Let's scratch that. So draw a big vertical line. We want to do something. Okay. Now on the right hand side of that, we're going to do something. So we don't here we represented the decimal quantities 0 through 15, right? However, let's say I have these 16-bit patterns. I don't want to represent numbers 0 to 16. However, I want to represent different numbers, same number of numbers, but different. I want to represent numbers from -7 to +8. -7. No. -8 to +7. -8 to +7. How many patterns are there? So write it down. So let's say right at the very top, say -8. Right at the very top, -8. All right, and then keep going down, and you'll see that you'll get +7 exactly when you get to, I think, that 15 thing, right? Against the F, you should get +7 because that's the number of numbers we have. Yes, unless I'm off by 1. I don't think so. Yeah, okay, all right. So This is also essentially what I'm saying here. It's a very subtle point, is that I can use the exact same bit patterns, exact same 4 bits that I had before, right? I can use that either to represent positive numbers, 0 to 15, or I can use that just as well to represent, 15 numbers that are a mix of positive and negative numbers. They just have to be different. They don't. So for all I know, you can come up with a really crazy scheme and say each one of those bit patterns represents a different prime number, right? That could also be one, right? Because if you can develop a mapping between binary bit patterns and prime numbers, right? The biggest challenge of great mathematicians over a long period of time, right? Because an ascending sequence of prime numbers like that, you can derive that. So you can come up with. So I'm saying let's not do anything sophisticated like that. Right? All we want to do is that we have these 16 patterns. We use that to represent 16 positive quantities. Now I want to use that to represent different quantities, right? Not necessarily prime quantities, not necessarily odd quantities, but I want to use them to represent negative and positive quantities. So what are those quantities? Well, you can only get 16 of those. Maybe I can represent 16 numbers from 0 to 10, and then negative 10, negative 50 to negative 56, right? There's 16 numbers. I can do that, but all of that is useless, right? Because the most useful chunks of numbers that we can represent is basically one contiguous chunk. So we say we're going to select a chunk of mixed numbers, right? So -8, right, to +7. So if we can represent that using those 4 bits, then we have a scheme which lets us represent both negative and positive numbers. So one way is sign magnitude notation, right? So in sign magnitude notation, what would be the numbers? So let's start at the 0, right? Let's start at the 0. So 0 and 0, all right? So let's write the zeros there. Okay, 0, yeah, 0. Yeah, thank you. All right, yeah, and then all 1 through 7 should be exactly the same. Yes, 1 through 7. Is this too fast for some of you guys? I think it's normal speed. I thank you very much, Hiram. He's right, drawing at the right speed for most of us, I think. Yes or no? Thank you.
Looking good.
Sorry?
No, it looks good. Thank you.
Great. Okay. All right. Now, now let's fill in the top of that. Also write sign magnitude at the top. Sign magnitude at the very top, so everybody knows. No, not that one. Yeah, but it's this one. This zeros and ones column. That's the sign magnitude. All right. So what would be -1 now? In sign magnitude, yeah, right? Yeah, go ahead, fill it in. Yeah, no, go on. Hey, where are you rubbing it off? Hiram. Okay, all right. So we're stuck here, right? Aren't we stuck? All right, and the reason for that is essentially the problem that Alexandria brought up last class, right? Because there's no way you can represent 8. You basically lost a number. You lost a number, and instead of 8, you got 2 zeros. Instead of 8, you got 2 zeros, right? So 8 is also a 0, right? So 1 0 0 0 is also a 0. Yeah. So and that's one of the disadvantages. And the other, so what we want to do really is that we want something natural to happen, right? So what we want something natural to happen. Natural meaning we have one way in which we know how to add things. It's just like if you know how to go to the left and right, that's all you know, right? So if you know how. Can you do everything using, can you execute the entire dance using just those two steps? That's what we're asking. And so what we want to do is, if I take the binary representation of 0 and subtract 1 from it, right? Subtract 1 from the binary representation of 0. Do I get the same value for -1? Because 0 minus 1 is -1, yes? In our head, 0 minus 1 is -1. Now, if I use my usual algorithm to do that, do I intuitively jump from 0 to the -1 in the other representation? That's what we're asking, right? So in Tue's complement notation, what we want to do is basically write out all of the, from 0 to 0 to what is it? 0 to 7, 0 to 7. Yeah, let's fill in 0 to 7, right? In Tue's complement notation. Yeah, 0 to 7. I will actually increase the font size just a little bit, okay? So, yeah, most of you are still there. Okay. All right. Yeah. All right. So, all right, 0 to 7. I'm actually winging it right now, off the top of my head. So we're all, things may not work out, and we will, unlikely, but if it does, you guys have to step in and correct it. Okay. So, so you want to do it that way? Okay. No. In Tue's complement, you want to do the same thing. Same numbers as you have on the left. You don't have to write. Yeah. So the same ones you want to do in Tue's complement, right? So you can use the same column, right? So you can use that already. You just need to fill out the representation. So let's start in the bottom and say it's 0 to 7. Let's fill out the 0 to 7. You can't see my mouse, right? If I move it over your screen, can you see my mouse? No, you can't, because I'm not sharing. So you want to start against the 0 in the Tue's complement column. You want to start against the 0 and then fill in 0, 0, 0, 0, because that is 0, 0, right? Yeah, there you go. All right. Now all the positive numbers are exactly the same. All the positive numbers are exactly the same. Great. Okay. Now, here's what we want to do. Right now, if we subtracted 1 from 0, what do you get? -1. Yes. Now, if you subtract, can we subtract 1 from these 4 zeros in binary? So we need some working area. Hey Hiram, is it possible to preserve the screen and open a new panel or something like that, so we can do a quick sum? Yeah, thank you. All right. So write down 4 zeros. 0, 0, 0, 0, and then say, -1, just like an arithmetic problem. Yeah, okay. Minus and the 1. Okay, there you go. All right. Now, horizontal line under that. And we're going to do our regular, second grade mathematics, arithmetic. We're going to do the subtraction here. And what would we do in arithmetic, right? So when we do this, so 0, you can't take a 1 from a 0. What do you do? What do you do? All right, you're going to borrow 1. You're going to borrow 1. Yes, you're going to borrow 1. But you can borrow 1 from a 0, because that's also a 0. Yeah. So you're going to borrow 1 from all the way up here. So what we're going to imagine is that obviously you can't take 1 from nothing. So you're going to imagine that, exactly. You're going to imagine that there's 1 extra bit out there, which is not really represented, right? It's not represented in the 4 squares, but there's 1 extra bit out there, right? So you're going to imagine that it's actually 1, 0, 0, 0, 0, not 0, right? So now you can borrow that 1 and turn all of these into 1, 1, 1, 1. Yes. Right? Actually, it's 1, 0, 0, 0, 0 minus 1 is going to get 1, 1, 1, 1. Yeah, that's what. Yeah, all right. Yeah. All right. So, yeah, there you go. All right. So, is everybody okay with that? So you got 1, 1, 1. Yeah. Actually, yeah. That thing actually helps, right? And in the last column, Hiram has 1, 0 and not 2. But it's actually 2, right? It's binary. It's 2, not 10. In decimal, we do 10. Yes. In decimal, if you do a borrow, it becomes a 10. But in binary, it just becomes a 1, 0, which is a 2. So 2 minus 1 is 1. So it's written a 1 there. Yes? Okay. Now we've discovered what -1 is. So you can write down the -1 there, right there. Yeah, -1 is basically, we got the -1 by doing our intuitive thing to 0, assuming that there was this bit. Yeah, okay, right? So yeah, there you go. Now if you take 1 out from there, you get the previous number. Yeah, 1 and then 0. All right. So every time, so now you notice here is a really cool thing, right? This is a really cool thing because we did this systematically. Now you can see that if you went all the way right to the top, right, and you keep adding 1, you're just adding 1, right? Adding 1, it does the intuitive thing. It's the most important thing. Adding 1 does the intuitive thing even at the boundary. When you go from 0 to 1 to -1, -1 to -1 to 0 to +1, it does the intuitive thing. right? Because the -1 is 1, 1, 1, 1. Okay, you add 1 to it, it's going to create all zeros but a 1 carry. That was the one you borrowed, right? That carry. But you can't represent the carry. So the carry is going to be thrown away. So you end up with zeros. So we actually exploited a physical limitation, an empirical limitation of storage systems, right? Because bits are stored, finite. Everything is finite. It's a limitation of our storage. We exploited that to come up with an incredibly beautiful and efficient way of representing negative numbers. How cool is that, right? I don't know. It'll take maybe some years, right? Before I don't know. Maybe some of you can already also, but it is a remarkable insight, right? Because it lets you do something that something intuitive that you're used to all your life since kindergarten, right? And says we have a binary representation and you can use exactly that and it'll work and it's internally consistent, right? And that's why we use Tue's complement, Alexandria, one of the more complicated reasons. But yeah, essentially, but you see that, here, addition, subtraction, everything is basically just exactly the same as what we've done. Adding 1 goes 1 to the right in that pattern. If you consider the pattern to be a ring, right? All of the patterns to be a ring, right? You add 1, go to the right, subtract 1, go to the left, and it'll work regardless of where you are on the ring. It will not work. It will not work if you do that with 1's complement, with sign magnitude. It works here, right? So so that means that your circuitry and a whole lot of things in the hardware side and software side, many algorithms, they're all much more simpler now. So things can happen more efficiently, right? And that is one of the reasons. And in fact, you can see, right? So you add let's see. We worked through examples last quarter. You can watch the videos, right? I think we've done this 2 or 3 times now, so I don't want to do it now. But what we did before was imagine that we wanted to represent negative numbers in decimal, but we couldn't use a minus sign, right? So we did the same thing as 2's complement in decimal, so that would be 10's complement, right? And then we use 10's complement to represent negative numbers in decimal. Right? So instead of saying, negative 5,200, we'd say, instead of saying negative 4,800, we'd say, 5,200, right? Because adding the 2, right? 4,800, because 4 digits, assuming 4 digit binary decimal numbers, I could say negative 4,800, yes? But I cannot use a negative sign. So I'll say, I'm going to use 10's complement and tell you 5,200, which is a positive number. But because it's 5,200, it's, I need to do the 2's complement in order to find out the real value. It's not 5,200. No number is greater than 5,000. Therefore, it should be, 10,000 minus 5,200, which is, negative 4,800. That's how we do it. I think it's a conversion thing, right? Do you want to work through one problem? You want to work through one problem here? On that, just that space is enough. One problem in which we convert a number from negative to positive in 2's complement. Give 2's complement notation. Do you want to do that, or are you guys happy to do that on your own?
No, could we do another one? Yeah, I'm still here.
Yeah. Okay, all right. Let's take a number. Let's take a number. Yeah, let's take a small number. 20, 25, 27, 27, 27. Yeah, 27. All right. So let's say we want to, let's say 27 bits. Oh no, 27. No, 32 is 5 bits. 5 bits is 32. So let's say negative 16 to plus 16. So let's say we want to represent the number negative 13, right? In using 5 bits, 5 bits. So you have to, for 2's complement, you have to know how many bits, right? If you don't know how many bits, you can't do 2's complement. Yes, because 2's complement depends on our ability to spot where the carry or overflow is going to be. If you don't know how big your thing is, you don't know where the overflow is going to be. Yes. Okay. So you have to know how many bits you're using for your representation in order to know. So 5 bits, 2's complement. Okay. So anytime someone says, what is this value in 2's complement? You got to ask immediately, how many bits? Because depending on the number of bits, the answer will be different, right? So negative 13 in 5-bit 2's complement. Okay. So that's what we want to do. So in order to do that in 2's complement, let's first find the positive. How would you represent positive 2's complement? How would you represent positive 13? How would you represent positive 13 in binary? Forget about negative now, right? Regular binary, how would you represent 13? So what time is it now, by the way? We got a lot of time. We got a lot of time. Oh, we've got almost an hour. So we got a lot of time, things to work through, right? Yeah. So I'm happy. All right. So yeah, 1101. Okay. Why did Hiram write 1101 for 13?
8 plus 4 plus nothing plus 1.
Yeah. Okay. Actually, it's 5 bits, right? It's not 4 bits. So fill in the missing bit also. Yeah. This is very important, right? Because in two's complement, what happens is that the leftmost bit usually tells us whether it's positive or negative. So if you use only 4 bits, now that looks like a negative number all of a sudden. Yes? Okay, so in two's complement, that's why the number of bits is very important. So it's 0, 1, 1, 0, 1. That is 13 in binary because it is 2 to the 0. That is, you know, Hiram, can you draw a little arrow? So that 1 is 2 to the 0, and then the 0 is the 0 next to the 1 is actually 2 to the 1, and the 1 next to that is 2 to the 2, right? So each digit tells you how many of those there are, right? So there's 1, 2 to the 0, there's no 2 to the 1s, there's 1, 2 to the 2, 1, 2 to the 3. So 8 plus 4 plus 1 is 13. Everybody okay with that so far? Okay, good. All right, great. Now what we want to do is, we know for all positive numbers, the two's complement version is the same as a binary. Yes or no? Right? All positive numbers, two's complement version is the same as a binary. Intuitive, exactly the same, right? That's what we wanted to do, right? So we got that already. Yes or no? Raise your hand if you said, yeah, okay. Okay, so all right. So now, so we know 13 is the version I want to use, but I want negative 13. So I want a bit pattern. I want a 5-bit pattern, which when added to this pattern for 13 is going to give me all zeros. I don't care if there's an overflow because the overflow is going to be discarded, but I want some bit pattern, which if you add to it will give me all zeros. Can you discover that? Okay, so write down 0, 1, 1, 0, 1 in the blank space on the right side, right? And you want to discover 5 digits, 5 binary digits, which when you add to this will give you 5 zeros, right? So you want to say, and draw those fill in the blank underlines, right? Fill in the blank underlines underneath. Yeah, right? So you want to add those 5, you want to fill in those 5 blanks so that when you add them, you get all zeros. Hey, thank you, Hiram. So he's always 1 or 2 steps ahead of me, which is, you know, making my life very easy. But you don't have to, by the way, okay? So nobody has to be as fast. Although it's nice to be fast, but you know, see, there are students who are slow, and then if you're fast, sometimes we miss it. Okay, so it helps to have a mixture of speeds when we do these things. Okay, so how can we devise a number that will give us all zeros? So I can show you a 2-step way, and you can always figure out a 1-step way or a way to how to do it mentally easily, right? 2-step way is to get all zeros. What I'll do is let me first find a number which will give me all ones, which is a whole lot easier, right? Find a number that gives you all ones, which is a whole lot easier. Then I know that the number that gives me all zeros is just one more than that number. Yes or no? Okay, so let's find a number that gives all ones, and then we'll add 1 to it and get our number. Is everybody okay with this? Hands up or no? Okay, all right. Now we know that the next number, if you add the next number above this, right, to the original number, you're going to get all zeros and a carry that needs to, you know, be discarded because it can't fit in the 4 or 5 bits. Yes or no? Okay.
I have a quick question.
Yeah.
How do you know that adding 1 to that number that'll give you all ones? If you like, how do you know that that'll work? By just adding 1 to whatever number gives you all ones?
No. Adding 1 to this number will give all zeros, right? Because 1 plus 1 is 2. That's 0, carry 1. That's 0, carry 1, carry 1. It's the same, exactly the same as adding 1 to 99999. You get 1 0 0 0 0. Yeah. Everybody clear on this? This is all very, very basic stuff, but you may have forgotten it because, you know, I don't know how many years is it since, you know, your kindergarten teacher taught this to you, right? Okay, so many of you may have forgotten it, but it's important. It's important basic stuff, and it's good refresher. You have to have this in mind. Now you can see this magic happen right in front of your eyes, that you have discovered a bit pattern that when you add to another bit pattern gives you all zeros, which is what you wanted. Yes? So that is now what is called your two's complement. The reason it's called two's complement is because a complement is something where you flip. No, it's not the complement with an I. A complement with an I is, you know, you look good and things like that, which is, you know, is a positive thing to say. But a complement with an E, which is really what is left over. Like in geometry, you know, you do that, you know, complement of an angle, right? Complement of an angle is what's left over after you take off 90 degrees, you know, that from 90 degrees, right? 90 degrees, that, you know, theta, and that, you know, 90 minus theta is your complement of the angle, right? So what is left over? That's your complement. And here, the complement of a number is what's left over from, you know, two's complement. In binary, this complement, one's complement is what's left over is after, you know, one's complement is basically flipping, right? It's flipping. And then your two's complement is adding one to the one's complement. That's your, one's complement is your flip, right? You add it and you get all ones, right? Two's complement is one more than, is everybody understand that? Yeah? That's our two's complement, how you convert from, you know, a number to, now you can go back and fill in that table. You get all those numbers and you know what those two's complements are, and see that that's your negative 13. You can fill in the negative 13 pattern in your, so you're going to discard the carry, right? No, this is 5-bit pattern. We're using 4, right? And for 4, well, basically you can go back to the table you had up there and you can fill in the rest of the values. They're all in two's complement, right? And you'll see that, there you go. Right? So you can fill out all the two's complement values also. Oh, you actually already filled it out. Okay. All right, great. So you can see that, you know, adding 1 to everything, it does exactly the right thing, right? So 1, 0, 0, 0, 0 is negative 8, but if you add 1 to it, you get negative 7, right? How do you know that's negative 7, by the way? If someone told you that's a, yeah, all right, let's do this problem also. You guys want to do this problem? So someone told you, oh, here, take the third number in that column, which is 1, 0, 1, 0. It's the third number in that column. No, up. No, further up. I see you're creating space. Great. Okay. Thanks. So further up, so you have the third, what's the third number? 1, 0, 1, 0, yes? Right. Now 1, 0, 1, 0 is negative 6, isn't it? 1, 0, 1, 0 is negative 6 in two's complement notation. But suppose someone told you, here's 1, 0, 1, 0. What is it? What is the value? How do you know what value it is? So one way to find out easily is look at the leftmost bit. That's the least significant bit, right? If the leftmost bit is 1, you already know automatically that it has to be a negative number, right? Look at the pattern in that table. You see all of the negative numbers have 1 in the leftmost bit, right? It's a natural consequence. You know why, but it's a pattern that you can remember without having to think. So that's why it becomes a calculus, right? Because a calculus is something that you can do without thinking. Right? And many people think that a calculus is, you know, dx by dy by dx and all those differentials and integrals and so on. No, calculus basically, it comes from the Latin word calculi for pebbles, right? Because that's how they, or abacus, right? In ancient China, that's how they count. So counting is using calculus. So, and why is it called calculus? Calculus is basically, is a word that says you don't have to exercise your conscious mind. You don't have to think like a human to solve this problem. You can solve it mechanically. Right? You can solve it by you shuffling pebbles around. You can solve it on an abacus, right? Without having to think. You can be crafting a melody. You can be thinking. You can be, you know, cracking a joke to your friend while solving a problem at the same time because your muscle memory can do this. Your muscle memory can solve this complex square root on an abacus. Yeah, I don't know if you've seen it, right? I have seen people who can basically carry on a conversation with you while they're solving a square root problem on an abacus. This is very remarkable, right? I think you can go to YouTube and find some videos. I have never seen it, but I've actually seen it's right. But it's possible. That is why this is that's why it's that, you know, that's, you know, people think that calculus is basically you have to have a lot of thinking, right? But really the whole point of calculus is to say how much of mathematics can you do without thinking? That is what calculus is, right? Calculus is the discovery of rules that let you do advanced mathematics by relegating as much of the routine work as possible to automatic things that you can do. That's why, you know, when you say, what is the slope of a parabola? You don't have to imagine this and do some conscious thinking there. You know, it's the parabola, I'll just differentiate the quadratic, you get a, you know, the slope, x squared, 2x, that's your slope, right? You do that mechanically without thinking. And that's why it's called a calculus. And exactly the same way you have propositional calculus and logic, right? Propositional calculus is that you can have very complex logical solutions, right? Someone describes a logical problem and you say, this is logically, that's a solution. And they say, wow, that's incredible. How did you come up with a logical solution? You must be really brilliant, right? No, actually, to be honest, I never actually exercised my conscious, brilliant mind to come up with the logical solution, because it is a perfectly logical solution. I did not have to use my brain, right? So that's the incredible thing, isn't it? The brain is only useful for non-logical things, really, because the brain comes with lots and lots of logical things so that the logic can be automated, can be taken out of your brain and done outside. Because if it's logical, it's predictable. Someone else can do it. And so that is the whole point of calculus, is to say, no, you had this beautiful solution. I didn't come up with it. It was a logical derivation. I started from this, which you wanted to do. And then I applied this calculus, which says at this point, this is the probability distribution that you have to follow, and so on and so forth. And this is a bunch of resultant candidates. You get to pick one of those, and you pick that, right? So it was basically a mechanical derivation. So, and that is propositional calculus, that, and you can say, and that is how, even when you get to 2C, and you find that you have to write programs in which you have complex conditions, right? Maybe you're not writing complex conditionals right now, but in maybe a couple of quests, maybe next quarter, right? Maybe next quarter, some of you may end up writing complex conditional statements, and complex conditional statements are, I hate them, right? And unfortunately, many students, even though they hate them, will try and keep doing them, right? Instead of doing things an easier way, because they didn't figure out that there is an easier way to do it, which is really, if you have a complex logical expression, you can actually look at it and apply some well-studied rules, okay? Like, for example, De Morgan's laws, right? De Morgan's laws, which you probably learn in school, right? So well-studied, well-known rules can be applied to logical expressions that look very hairy and complex on the surface, but you can reduce them, right? Using predictable rules, and ultimately end up with 2 or 3, conditions that you can just look at and know immediately what's going on, right? There are so many situations where that's happened, and then you will be able to simplify your own. And, strangely enough, it's not just restricted to computer programs, right? When you get good at logical transformation, propositional calculus, right? Transforming one logical implication into another equivalent one, which doesn't look identical on face value, but they're exactly the same. You can prove that, sine squared A plus cos squared A equals 1, right? They don't look the same, but you can prove that it's the same. And but once you know that, you'll find that it makes a lot of things easier, right? And not just in computer science or mathematics, but many places where that call for logical inferences in life, right? You may not be consciously employing that logical thing that you learned in CS2A or magic in mathematics, but subconsciously that factors into your neurons, and the way you make decisions is you'll be solving simpler problems in life, because you'll know that the simple problem actually solves a bigger problem. And you'll see a lot of people around you, right? They will be solving really, really hard problems, which are essentially don't have to be solved if they solve a simple problem, but they haven't seen the simple problem. So they're solving the harder, they're threading the groove. They're, grinding away. And a lot of people spend a lot of hard work, a lot of money doing hard work when they don't have to do hard work, right? If they had just mastered some simple concepts that makes that's what I say, people who are unable to simulate reality have to live through reality in real life, right? Which is harder many times, right? So it's much better to just sit down, take your time. Now, when you are 2A students, you have a lot of time. Don't overload yourself with 5 courses, 90 units and crazy shit like that, doing many things that are not going to be useful to you, right? So just sample things, find out what interests you, and spend a lot of time just finding out more and more things about things that interest you and that are going to be useful, because many things that people invest time in, they're not going to be helpful to them eventually, right? And these little courses may not matter so much, right? But I've seen many people that solve very big problems that span 2 or 3 years, when I can tell that what they're going to do is not really going to solve their problem or anyone else's problem, but at the same time, there might be good things to trying things out, even if it's not going to work, because it builds skills, right? Because sometimes we solve these problems. Many of these may not have direct applications in your quests or in your exams, or even in programming contests that you have out there. But I think that these will be useful to you, right? In your programming. I don't know, if you do someone else's CS2A, I don't believe that many other CS2A sections spend an entire week on data representation like this. Yes? I don't think any other class gives you a data representation primer, but I think that this is like so critically important because this is going to play a part in every single thing you do in 2A, 2B, and 2C, especially if you stick with me, that it is totally worth spending 1 week here in order to save a lot of time later on. And that is what we get here. We get the advantage of the luxury of being able to spend time doing what we want later on rather than doing what we don't want, because this is stuff you don't want to be doing later on. When you get to the juicier ground, you want to be playing the juicier game, right? So let's get this out of the way. Is everybody okay with this so far? See, you added 1, you get all zeros, you get the carry, you throw away. That's your two's complementation. That's how we translate from decimal to binary, binary to any other conversions you want to go through, you can go through now. Otherwise,
if we have time today, could we do a negative decimal conversion?
We have time. I'm pretty sure we have time. What time is it? We have a lot of time, Alexandria. We can do that, right? Yeah, just call out a number. Hiram can. Hey, Hiram, you can save this entire screen. You can save the screen, right? You can share it on Reddit if you want. I don't know. It's not. There's no. This is very little notes, but maybe.
So yeah, this is in Microsoft OneNote, so I can just export it as a PDF.
Yeah, yeah.
Easy.
No, I know you can. But I was thinking, is it possible to, if you just posted this on Reddit, is it possible for a random student to just look at it and how much information can they get out of it? Maybe you need a little bit of annotation. Well, before you post it, just scribble some notes here and there. Okay.
Okay.
All right. Thanks, Alexandria. Hey, you can open up a new screen now. Alexandria has a problem. We can work through that.
Yeah, just like something easy, like negative 4.5.
Oh, negative 4.5. You want to do a floating point and a negative number?
Yeah.
Okay, yeah, that's fine. Well, all right, so we're not going here. I'm not going to do the official one because the official one is pointless. What I want to do is, suppose we have this challenge. So if someone tells you negative 4.5, represent negative 4.5, right? In binary, how would we do that? That's essentially a question, isn't it? Because other things they're all frills and specific details we can add later. So so Alexandria says we want to represent negative 4.5. How do we do that? How do we do that? Well, first of all, we know already that it is a fractional number, right? It's a fractional number. So we want to be able to represent it as a floating point, right? So it's got to be a floating point number, which means it has to be represented as I'm trying to think of we will do that. So floating point. So we'll have a matriz of -4, and a 0.5 is 2 to the -1. Yeah, okay, let's do it like that. All right. So -4. Yeah, we can do with a 8-bit floating point. All right. So in practice, floating point numbers are not 8-bit. Okay. No realistic computer is going to give you a floating point number that's only 8 bits long. The smallest floating point number I know, even from the earliest C programming days, is I think it's 4 bytes. That's already 32 bits. So, but for the purpose of the class, we're going to represent that using 1 byte floating point number, a 1 byte number, and in that 1 byte number, let's just say that can we use? Yeah, let's use 3 of those. How many bits are in 1 byte? I'm going to ask you guys a lot of questions here. Okay, how many bits are in 1 byte?
8.
8. Okay. All right. And someone other than Neil now, tell me. Choose. Right. How many of those 8 bytes do we want to use for a mantissa, which is the non-fractional part, right? And how many bits do we want to use for the exponent, right, of that number? So just split it up into 4, 4 and 4, or 5 and 3. Just tell me some numbers. Someone else other than Neil.
5 and 3.
5 and 3. Thank you, Agnes. Okay, all right. So under
Why
that,
not?
that's right. 5 bits. 5 bits for the mantissa, and 3 bits for the exponent. Yeah.
Is there a logic to how many bits are used for the mantissa and for the?
Yeah. So if you get to design a chip, you join ARM or Intel and design a chip, and you say this chip is going to use a floating point number 16-byte floating point numbers, then you do something. You can design your own floating point number, right? In fact, maybe you have a scientific application later on, in which you know for sure that numbers span a certain range, right? That you can design your own floating point representation to make other things efficient. Very, very rare situation, but I'm pretty sure that there must be engineers at NASA or JPL, who do these things, right? Because, when you get to the level of programming things on rover or things that you send to Mars or Moon, you can't bank on many of the luxuries we take for granted now. We have to do things at the very, very bare bones level. And in fact, I remember when I was at SRI, there was some program that we needed to write into a module that was being sent to Mars. And we could do a lot of really sophisticated things, but the specifications of NASA are so strict that we only could do things on an Intel 8080 processor when everybody is playing around with Pentiums. So some very, very basic processor that is shielded by some lots and lots of lead, maybe, right? To prevent cosmic rays and alpha rays from hitting it. So you can do very, very basic stuff. And all right, so I don't know where we got started talking about that. All right, so 5 bits for the mantissa, 3 bits for exponent. And let's also say that, both the mantissa and the exponent can be negative, yes? Because negative 4.5, what is negative 4.5? Let's write it out in binary. What is negative 4.5 in binary, right? If I wrote down negative 4.5 in binary, right? Forget about all the representations. As just a like decimal, right? What is negative 4.5 in binary? Negative 4, what is 4? What is 4? 100, yes? 100 is 4. So in negative 4, if you didn't have all the fancy representation, you're going to say negative 100, yes or no? So yeah, yeah, thank you. I didn't even look at the screen. Hiram, you actually wrote it out. So that is negative 4.5. Is everybody in agreement with me so far? Okay, so we want to represent that. And we can already see that well, on the right side, it's a negative number. It's a negative number. Okay, so I'm going to write this in a slightly different way. I'm going to write this as 1001 times 2 to the negative 1. This is just, yeah, and it's got to be negative 1.
What was the 0.51 again? Sorry.
Oh, because if you were dealing with decimals, the first number after the point is signifies the 10 to the negative 1 place, yes?
Ah, gotcha.
10 to the negative 1, 10 to the negative 2. So you have ones, tens, hundreds, and so on. You have 1/10ths, 100ths, 1,000ths, and so on the right side of the negative point, yes? On the right side of the decimal point. This is called the radix. I want some feedback, okay? Because you guys got to tell me, otherwise I can't move. Right? On the right side of the radix, you have decreasing powers of 10. As you move to the left, you have increasing powers of 10 in decimal. Yes or no? Yeah, okay. In binary, we have increasing and decreasing powers of 2, right? So 0.1 is 2 to the negative 1, which is negative, 0.5. 2 to the negative 1 is 1 over 2, which is 0.5. Yep. So that is your negative 1001 times 2 to the negative 1, yes? So now if I want to transmit the number negative 4.5 to Alexandria over the wire, right, in 2's complement form, in floating point form, I'm going to send her an 8-bit number, right, in which the first 5 bits will encode the number -4 in 2's complement. It doesn't have to be, it has to be an agreement, right? Both Alexandria and I have to have a prior arrangement saying that, when you split the number up, you have to split it up as 8 and 3, because that is what Agnes decided, right? So we have to understand that before, because if I split it up differently and she split it, his number's lost, right? So we both have to have the same understanding that it's 5 and 3, and also that both of those are in 2's complement notation. That is, the mantissa is in 2's complement, the exponent, that's also, because, we could have a different agreement. I could say, well, that's in 2's complement, that's in sign magnitude. Or I could say both in sign magnitude. I could do anything, right? Some other fancy notation. So the agreement that we have in place is that both in 2's complement. Yes, thank you so much, Hiram. Okay. So now let's go ahead and convert the negative 1001, right? So negative 4. Basically, essentially, you want to say -4. what is -4 in 2's complement, right? -4 in 2's complement. So you start with a +4, which is 0, 0, 0, 0, 1, 0, 0. How many bits are we using for? We're using 5 bits. Using 5 bits, yes, for the Mantisa. So, all right, so start with 0, 0, 1. Yeah, right? Right, and then you add 1 to that. And that is -4 in 2's complement. Is everybody okay with that? Yeah, everybody okay with that? All right, so we got the first 5 bits of our floating point already right there. So right, you can create a box with 8 cells, and we got the first 5 cells now, right? And you can fill it in 1, 1, and 0, 0. Now we want to find the exponent, right? This is -1 in 3-bit 2's complement. Actually, you divide it up equally. Oh, I see, you're doing it the right way. It's just, that's really the correct way to divide up I used to do that in class. I don't know when Agnes was there, and did you do face-to-face or online, Agnes?
The Java class?
Yeah.
Yeah, it was online, and then I went on campus one time for the project that we were doing.
Yeah. So, because that was, it just brought back some memories from several years ago. When you have you have a slice of a cake, and you have to divide it for 5 people, or 4 people. The right way to do it is to divide it into 2 equal halves first, and then divide the 2 other equal halves into 2 equal halves, right? Because when my little, so when other people's, when you have the first little kids do it, right? They do it differently. They'll actually start with the biggest piece first, and then as the 3rd piece is cut off, you have only a tiny sliver left. So which we find with chopping of bits is actually easiest when you chop it off into halves. All right, now someone convert the 1 into, it's actually a -1, isn't it? It's 2 to the -1. So we want to convert the 1 into 2's complement, -1. So we want the 2's complement -1 and put it in there. And that is our 8-bit -4.5, which is what Alexandria wanted. Does that make sense, Alexandria? Yeah. Now,
Yes.
obviously, this is not enough, okay? This is not enough. You just have to pick up numbers out of thin air, just like Alexandria did. Just pick up a few other, like 3 or 4 other numbers, right? Work them out on your own on a piece of paper. And then what you can do is share them on Reddit so that some other people who have done a different set of numbers, they can cross-check yours and you can cross-check them. And then you can share this, right? And do it on Reddit and rather than on Discord or something so that you also get points for these things, okay? There you go. Does that make sense? That is -4.5 in floating point notation, where both the mantissa and exponent are stored in 2's complement notation. We actually covered a lot of ground, right? We covered floating point, we covered 2's complement, we covered hexadecimal, and a lot of things. So I don't know if you guys are all clear on everything. It'll take a little bit of time. That's fine. You still have until Sunday, right, to keep fighting with data representation issues. But it's really good to get it completely behind you so that you don't think about this consciously anymore. Right? So you can start working on, because I can assure you that there is a great deal of fun, right? There's a great deal of fun downstream, and you'll miss out on the fun if you're being stuck with niggly basic bugs, right? Basic bugs are no fun at all when you're dealing with advanced stuff, right? Because with advanced stuff, you want to have advanced fun. And basic bugs will take you a lot of time to fix when you're, that's the other reason, right? Basic bugs only take you like maximum of 2 or 3 hours now to fix. Basic bugs will take 1 or 2 weeks for you to fix. It's counterintuitive, isn't it? It's counterintuitive, but you will see that it's true. A basic bug, especially data representation or some simple error, will probably take you 1 or 2 hours to fix now, but it's a big chance that will take you a couple of weeks when you're doing 2C. And the reason for that is that you're totally not looking for it, right? You will never, ever spot an eraser right in front of your eyes if you're not looking for it. So you will not be looking for basic bugs in a few weeks. And then what happens then is that it's a pity because it'll just take time away from you. Lots of time away from you from enjoying the good stuff because you'll be fighting this nonsense and you'll give up, right? Many people give up at that point because they haven't got to the point where they're facing the juicy bugs, right? So is everybody clear so far on all the things we've done? Yeah, good. Joshua, Agnes, Alexandria Hiram, you've been driving, so that's great. Neil, all right. So the people that I need to get feedback from really, I think I would be looking for feedback from Jared, Francis, Fernando, Musa, Jack. You guys, are you guys, Madison, are you here?
Yes.
Okay, great, great. Okay, so you should feel free to be more vocal. People that don't have a camera and all, right? It's fine, but you got to be more vocal in class. At least be breathing really loudly, okay? Fernando, I'm not happy with just your, thumbs up, okay? Because, I can't see the thumbs up in the recording and all. It only comes up in the Zoom screen. It disappears in YouTube. You got to say yes or no, right? You just can't say yes because you don't know who said yes in the recording. Because, hey, Fernando, I'm Fernando, I'm okay with this, okay? You got to say
okay. Yeah.
or, you can do what Jared just did. Turn on your camera. That's much better, all right? So we know we're looking at you and you're looking at us. Francis, I have no idea if you're even in class. Okay.
I'm here. I'm here.
Okay. Jack, Musa.
Yeah, I'm here.
Who was it? Jack or Musa?
This is Jack.
Okay.
I'm here as well.
Okay. You guys have to keep speaking up all the time. Okay. I'm not even looking at chat. Nobody's going to be looking at chat, right? I'm not recording the chat. I'm not saving it, anything, right? So you got to speak up or can have your camera on. No questions? What time is it? We have a lot of time. I'm pretty sure we have a lot of time. We have a half hour, right? We have 20 minutes. We have 20 minutes.
I have a question. Won't the exponent always be negative?
No, what if I had to represent 45?
Oh, I see. Okay, so it's negative because negative 4.5 is negative.
Yeah.
Okay.
So, yeah, so sometimes, yeah, that's right. So the exponent can be positive. So you allow for it to be, you span a range. And so here's an interesting question for you to noodle, okay? We know that in 8 bits, you can only get 16 patterns, yes? 16 possibilities, you can only represent 16 numbers, yes? In 8 bits. You cannot get a 1-to-1 map beyond 8 and 8. All right, so however, if you do floating point representation, the range of numbers you can represent using 8 bits is now larger. Yes, because your exponent, if you use only 3 bits for your exponent, you can go all the way, for 3 bits, you can go all the way from a negative, what is it? For 3 bits is 8, so you can go from negative 2 to positive, no, negative, you can go from negative 2 to positive 3. You can go from negative 2 to positive 3, yes? Negative 2, negative 1, 0, 1, 2, 3. 8 patterns. Oh, negative 3 to, yeah. So someone tell me this. What are the bit patterns? What is the range of numbers you can represent in 3 bits? If you went negative and positive, you have in 3 bits, you can represent how many patterns? 8, yes? So 8 will have to, if it was 2's complement, will span, if you had to span an equal number of negative and not negative, I should get out of the habit of telling you negative and positive numbers. So it's not negative and positive. If you say negative and positive, we're not speaking like mathematicians, right? Because negative and positive rules out the 0. You should say negative and non-negative. That covers the whole range because 0 is a non-negative number. It's not a positive number. Right? So say you have an equal number of negative numbers and an equal number of non-negative numbers. You go from negative 3, negative 2, negative 1. Well, actually, you start from negative 4, right? Negative 4, negative 3, negative 2, negative 1, and then 0, 1, 2, 3. 4 positive, 4 non-negative numbers, 4 negative numbers, right? Negative 4 to negative 3, and then 0 to 3. So that's a range. Is everybody comfortable with that? In 3 bits, 2's complement, you can represent numbers all the way from negative 4 to positive 3. Positive 3 is 0, 1, 1. Negative 4 is what? 1, 0, 0. Yes? Well, you can work it out. You can work it out on a piece of paper later. Convince yourself, right? And if I'm wrong, you should come back and tell me, hey, you were wrong. Okay? But you should show it out. Anyway, if you can have an exponent as high as +3. So you're essentially saying, I can have a mantissa times 2 to the 3. That is the biggest number you can represent. So what is the biggest positive mantissa you can represent? The mantissa has 5 bits. Yes? Are you guys following through with me? Because this is an interesting chain of thought. It's an interesting chain of thought that is totally worth coming with me. It's a walk, right? It's like a walk in a theme park. If you come with me, you'll see some great wonders. Okay? So here, 8 bits, you have 5 bits for your mantissa. You can represent a total of 32 numbers. There's 2's complement. So you're going to go from -32 to +31. So the biggest positive mantissa you can represent in 5 bits using 2's complement is +31. Yes or no? Hands up if you're yes. If you understand that.
I don't think that's right. I think that it's -16 to 15 because the range would be 32 because 5 bits, 32 digits can be represented.
Thank you so much, Hiram. Thank you. 5 bits, right? So -16 to +15, right? So 5. Thank you, Hiram. Okay, 5 bits. 15 is the biggest.
But it's 32 total, or 31. 31. Total,
you have to include 0.
Is what you're saying?
Yeah.
Include 0.
Include 0.
Oh yeah. Right. Okay.
So 15 is the biggest positive number you can represent in 5 bits. And the biggest positive exponent you can represent in 5 bits is 3, which is 2 to the 3 is 8. So the biggest number you can represent in floating point using 8 bits, using Agnes's split, 5 and 3. Yes? 5 and 3 for floating point is 15 times 2 to the 3, that is 8. 15 times 8, that is 120, isn't it? 15 times 4 is a 60s, 120. So you can go all the way up. So you're saying with floating point representation, you can represent a number all the way up to 120 using just 5 bits. Using 8 bits, right? But 120, actually, can you represent all the way up to 120? Oh, what's all the way up to, and what's the biggest negative number? Oh, well, you know what? Our choice of exponent and mantissa was unwise because it doesn't matter. So what I was trying to get at, I'll tell you what I was trying to get at, and then you can work out a better split of that. So what I was trying to get at was that the biggest number you can represent in floating point is bigger than the number you can represent in 8 bits. Right? In 8 bits, you can represent only, the biggest number you can represent is, you can only represent 256 numbers. But the biggest number you can represent in floating point is actually bigger than 256. The smallest number you can represent in floating point is actually smaller than 256. So the range of numbers you can represent in floating point is actually bigger than just the 256 numbers you can represent. So why is that? I don't know if that question even made sense, but it actually does. Doesn't the question make sense? Right? Let's say that the first step in here is just making sense of the question, right? So why do floating point numbers let you represent a bigger range of numbers than the actual number of bit patterns allow us to?
Wouldn't it be because it skips some numbers?
Yes. Who said that, by the way?
That would be me, Hiram.
Hiram, yeah, okay. All right. Yeah, Hiram. Yes, that is true. But I want everybody else to basically think about this and don't shed any more light on this, Hiram or Neil, or right. Some of you have got this, I think, already, but think more about this. And because it's a paradox, isn't it? It's because you're saying 8 bits, there's only 256 possible unique patterns you can get out of it. There is no way you can get 256 different shapes. So if you said each shape was a unique number, you can only have 256 numbers. But here you are in floating point. You're saying that you can represent numbers from that represent a bigger range than 256, right? Let's say -512 to +512. That's a bigger range. There's a 1024 numbers there. How can you represent that? So it's an interesting question to ponder, and I think it also is an enlightening question to make you really appreciate the nuances of this representation, so that later on, when you get to do machine learning and all that, when you actually have to grapple with data representation issues, right? Do I need to use floats or integers or doubles for this quantity which is being recorded and sent to my model for training, right? or examples. What is it? How many digits? All these things will actually factor in them, right? And you'll see the kinds of decisions being made. Machine learning programmers, right? The kinds of decisions being made by machine learning programmers who are solid on data representation issues are different in character from the kind, because both people can solve the same problem, but the kinds of decisions and the efficiency you'll get out of someone who really knows computer sciences is it's a different ball game, right? So because they know what happens at all. So that is why. So if you ponder this question, you'll get a really close to understanding, to appreciating what data types to choose for later things that you'll be architecting and building. Right, and there are holes, and the beauty, like Hiram said, right? So you don't represent everything; you only represent some numbers here and there, so that you only represent 256 possible numbers, right? But still there. But how are they distributed and things like that? You can start thinking about that in your spare time. But those are the essential aspects of data representation. Right? I'm not going to go into the details of ASCII and how you can represent ASCII letters and binary and so on and so forth. It's all very straightforward. You just Google for it, or just modules, right? I actually talk about that in module 0. You can read module 0, and I'm pretty sure that Michael also talks about it in his notes. So you should feel free to. If you have any questions, obviously you can ask. But otherwise, we've covered a lot of data representational issues in class. We have about 10 minutes left. If you guys like, what I can do is basically step off screen so that, give you some space so that I'm not here, breathing down your neck all the time. So I'll just step off screen. I'll, turn my camera off so that you guys shouldn't go, right? Let Hiram have his screen up here. And then what you guys can do is basically chime in with each other and talk to Hiram, and maybe you can solve problems, interesting problems, little problems, or you can just, use and do that, right? Chat with each other. And would you like that? Would you like that for 10 minutes? Because we didn't have a break and all. You guys, maybe you're, you need a short break, and you can have a relaxed conversation amongst yourself. But if I'll be around, so that if you need me to come and clarify anything, you can just call me, okay? I'll just be around here, and I'll come back.
Do we just yell really loud?
You don't have to yell loud too. You just call me. I can hear you. I can hear
okay.
you. Yeah? Okay. All right. I'm going to be off screen. So I won't be looking at you guys. So just don't, even if I'm looking at you, shouldn't let that cramp your style. Okay. Just feel free to talk and converse and appreciate this on your own. I'm going to step off and I'll come back just before class. Okay. In other words, if you guys have to step away and go off before then, thank you for attending. Was this class useful? Right. Raise your hand. Was this class useful to you today? Yeah. Okay. Great. Thank you. The rest of this week, don't forget, okay? We haven't finished data representation. Keep reading, don't start programming already, okay? Because anyway, even if you quest now, your quest scores don't count, because on the 1st of October, the scoreboard will get wiped. The 1st of October, April, and so on, 4 times a year, the scoreboard will get wiped. So if you accumulate scores now, they're not going to count. You got to submit all your source code again after October 1st. Don't even quest. You've got a lot of time to code. So just focus, keep reading, rereading, looking up the net, reading Wikipedia, data representation. Just focus on data representation. How can you get everything into ones and zeros, right? If you cannot see anything, right? If you're blind and the only thing you can tell is whether there is a sound or not, right? That's essentially what we're trying to say, isn't it? Right? So ones and zeros. How can you code everything in this world? Everything, right? Everything. Even things that people think are intangible. Can you code them in ones and zeros? That's a real challenge. And if you keep thinking about that, then next week when you start coding, you'll be much better prepared to handle the nuances of how programming languages let us do that. All right. So thank you so much. I'll try and be back just before we end the recording. Just feel free to converse. Thanks.
Hey, Hiram, thank you for all the notes. It's really helpful.
You're welcome. Okay, maybe I should go back and do like the annotations he talked about.
That was really,
what would be helpful? Like,
are you gonna post it on Reddit or?
Yeah, I will post this on Reddit, but I need to like figure out what I need to annotate and what I don't.
We also have a class notes document.
Yeah, we started a Google Doc.
Where is that?
There it is. Are you on the Discord?
Yeah, I am.
Okay, great. Yeah.
Yeah, I saw the doc in the chat. Do you want me to like
Yeah, just put in this in resources.
Yeah. Let me open that link actually.
Yeah.
If you post to Reddit, I think maybe we can just link to the Reddit post from the lecture notes, so it doesn't like, you know,
Okay,
get
that makes
super
sense.
long
So I
there.
will just post it to Reddit and then you can link it.
And then we can
That makes
collectively
sense.
update it.
Okay,
So
that works too. Any annotations
awesome.
that you think would be helpful? Because I have no idea.
You know, you were already very helpful. So this looks great to me. I just need to go back and digest everything.
Yeah.
It's probably gonna take another day because I actually didn't do like floating points before, and so I was like, oh wait, gotta switch gears.
Yeah, I looked through the entire module and I was like, oh, this
Mm-hmm.
makes sense. Maybe I should move this into the other. I don't know. Do we want both of these or do you just want the data representation one?
I think both of them
Would both of these be okay?
Okay. I could just put this one into the bottom of this one. That might be better. Okay.
Yeah.
Let me just copy it then.
Whatever.
Thanks.
Whatever that works.
Just trying to figure out how to best organize this.
Yeah. And then we're also talking about
X. Okay.
We're also talking about getting together after 8 p.m. today to just go over this one more time.
I'm not opposed. I don't really know what I would want. Okay. There. Now it's all in one sheet.
I'm gonna put the Discord link in one more time.
Okay, that sounds good.
In case anyone else wants to.
I'll draw a little. Maybe I can move this bit over so that it doesn't block it as much. I think I just missed the exponent. That's fine. Yeah.
Actually, does anyone want to explain the exponent part of the floating point rep to me? Because that has
I have the most trouble with that too.
Yeah.
Okay, I think I get it sort of well.
Okay.
So basically the exponent, the way it works is that it literally just stores an exponent that works the same way as like the base 10 exponents. So you know how like if you multiply by any power of 10 in decimal, then if you have a number like 1, 2, 3, 4, 5, and you multiply by 10 to the negative third, then your decimal point will go 1, 2, 3 places, right? So you get 12.345.
Okay.
Without this. And in the same way with binary, if you have 1, 0, 1, 1, 0, 1 times 2, because it's not 10 anymore, each thing is a power of 2. So now we are multiplying by 2 to the like fifth or the negative third or whatever, right? I'll just do negative 3 again. Then we get 1, 2, 3 again. So we get 101.101. Now the difficult part is that this we would need to now like figure out what the heck it means. So 101, wait, that would be 8 plus 1, so 9. No, wait, no, bruh, that is not it.
Wait, so the exponent tells you where to put the radix, right? That's what that
would be 5 point. Yeah, the exponent tells you where to put the radix, exactly. Okay. And then 101 would be
the radix being the dot, right?
Yeah.
5.
Yeah,
This
we're
would
on
be
the same page.
1/2. This would be 1/2 plus 1/8. Shoot, what's a half plus an eighth? 5/8, but like
0.125 is
5 divided by 8, 0.625. So this would be 5.625, 101.101 in that. So that's how the exponent works and like why it's pretty easy. And then all you need to do once you like understand that is that you basically just take this and you use 2's for both. At least that's what we did there. So our exponent was -1. So 1 in 3 bits would be 0, 0, 1. And then you can look at this and it's super easy because you just need to add 1, 1, 1 to it to get the zeros because it's the same as adding 1 to all, right? Does that make sense? And then you get the 1, 0, 0, 0, but we don't care about this. It's like an extra carry. So this is our 2's complement for 1, which means that it would be -1. I don't know. That's how I like to think about it. Like the 2's complement of a positive number is the negative number. So, and then we can just put this 1, 1, 1 into the exponent, and that's -1 for the exponent. So in this case, this literally reads as this number, which is 1, 1, 1, 0, 0, which is in 2's complement once again. And since it's a 1, at the frontmost digit, the leftmost digit, that means that we know it's negative because it's in two's complement. All the ones that have a 1 at the front are negative. And so we can just convert it into what it actually is. So let's, and that would be, as we did it with -4.5. So it should be -4. Wait.
So just to be clear, both the mantissa and the exponent are in two complement, right?
Yeah, both the mantissa and the exponent are in two's complement. What I'm worried about right now is like, wait, does this actually like, let me see. Because if this is -4, like, I guess I don't understand this as well as I thought, because like, yes, we have -4 plus 2 to the -1, but like, if that's all it is, then we can only.
Wait, where?
Because like -4.5 would be -4 plus -0.5, right? So I don't understand how this represents it actually. Shoot.
Yeah.
Shoot. I think this is like -4, not -4.5.
Yeah, that's -4. Wait, what?
Yeah. Because
yeah, that's
sorry,
-4.
it's so confusing. I think he messed up.
Everybody's like, wait, what?
Because this mantissa, like, if we're doing scientific notation, the mantissa would be the entire like number, right?
You lost me.
So like
I thought it would be like 45 and
right? Yeah.
And we're
now that I think about
adding.
Yeah.
So we would we would have to get -45 and then.
Well, he didn't really explain how to pick how many bits for the.
Yeah, he didn't.
Right. So
for -1, it should be pretty easy.
All right, I've got to go.
Picking is just arbitrary, right?
Yeah, but there's some that will, like didn't he say that it was unwise? I guess that's why he said it, because I lost him halfway.
The thing that I think he was,
so.
I don't know exactly what he was talking about, but like the thing that I noticed is that the floating point notation, right? Like with our method actually has like less total like thing than just a normal byte's worth of data.
Yeah, because
but it includes some decimal. Yeah, right? Because of the exponent. Like, so we actually can't represent a larger range. It's just that some of the decimals are now included while it excludes some.
You can represent a larger range though, because if you make the exponent positive, then you could,
you'd think so, right? Because like 2 to the 3rd is 8, right? And then our biggest number that we can represent using this, if we're using 2's complement for both of them, would be 15. And then the biggest exponent we can represent is 2 to the 3rd, which is 8. So 15 times 8, which is 120, which is actually less than 127, which is what you get with a normal byte in 2's complement. Right? Because a normal byte in 2's complement would have 2 to the 8 representations that you can use. And 2 to the 8 is 256. So half of that minus 1, so that we can include 0.
So why don't we just see if we can get a number bigger than 256? Actually, do you want to do this so everyone can see? If you scroll down a bit. Why don't we just see if the biggest possible number that we can represent with 5 bits for the mantissa and 3 for the exponent is larger than 256? Because then we'll know that we can represent a bigger range.
I did that.
You did?
Yeah, that's what I did. That's what I said. The largest number we can represent would be 15 from the mantissa. And then 3 from the exponent, right? In 2's complement.
Okay, could you like write it out though?
Okay, yeah. So the mantissa, the largest number that we can represent, if we are going back to up here, right?
Yeah.
It would be like 0, 1, 1, 1, right?
Exactly.
So we would have
wouldn't it be
0, 1, 1, 1, 1, right? Yeah. And then that would be 8, 4, 2, 1. 8 plus 4 plus 2 plus 1 is 15.
Right.
So that's the biggest number that we can represent there. And then the exponent, we have 0, 1, 1, which is 3.
Okay.
So the biggest numbers that we can represent in the mantissa and exponent are 3 and 15. And this means 2 to the 3rd. So 15 times 2 to the 3rd, which is 15 times 8, which is, as he said, 120, which is actually less than that 127. But the reason that
I thought you said the exponent moves the radix that many places, right? So wouldn't it be moving it 8 places to the right, and therefore creating 8 extra place values, and therefore boosting the.
But we're converting it into decimal, right?
Yeah, but doesn't it? Wait, what? No, I thought. Hold on. When you did the other number, you moved the decimal, or you moved the radix to the left, right? Because it was a negative exponent.
Yeah, so
And then
if we want to do it,
evaluated.
oh,
That was in
okay, so I
binary
see what
though,
you want.
right?
I see what you want. So I'm doing the same thing. I'm just converting to decimal early. So if we convert
Okay.
it, if we stayed in binary, then what we would get is we have this, right? And then we have the 3 places. It's 3. So we would move the radix 1, 2, 3, right? So we would get 1, 1, 1, 0. Oops, 1, 1, 1, 1, 0, 0, 0, right? And that would be
Right.
1, 2, 4, 8, 16, 32, and 64, right?
Right.
So let's see what that adds up to.
Oh.
64 plus 32 plus 16 plus 8. Wait, does it include that? Yeah, it does. Is 120, like I said before. So
Okay,
it's
gotcha.
the reason that I multiply is because, and that it doesn't work that way, is because this is a 2 and we're in decimal. So when we're in binary, multiplying by 2 to some exponent will shift the radix because it's the same as the power, right? The base is the same as the, shoot, what's the name?
What?
Oh yeah, the base is the same as the base.
Okay.
Because yeah, we're normally decimal is a base 10 system and binary is
Wait,
base 2.
can you just say exactly what you said again one more time?
Yeah, so when we have binary, multiplying by in decimal 2 to the 3rd,
Yeah.
so like if we're thinking in binary, multiplying 2 to some exponent, which in binary would just be 1, 0, right? 1, 0 to some exponent, which is, again, it looks like 10 for a good reason, because they're both the first time that you get one more in the next digit. Multiplied by 10 to some exponent, say like 3, so that would be 1, 1. Then it does shift it.
Okay.
Wait, shoot. Yeah, that makes sense,
so,
right?
So 2 to the 3, that's what that is in binary though, right?
So yeah, 0, 1, 1 represents 3, and since it's an exponent, 2 to the 3 in decimal. In binary, I don't know. Because like, I'm still trying to figure it out. Like, because this would be how you would represent 2 to the 3 in binary. But I don't know how that affects the radix. I guess, oh, I know what it is. Okay, so I was thinking like, this looks like 11. No, it's not 11. That's still just 3. It's just represented differently. So it was my mistake. So yeah,
okay.
It is still 3 digits moving. Okay. So yeah. Yeah, it's a cool thing, like that you have to remember that you're what base you're in. So this is in base 10 and this is in base 2. So the radix moving requires that your base be 2, and in this one it would require your base to be 10, which is why this isn't like 15,000. 15,000. 15 times 2 to the 3rd isn't 15,000 because we're not moving the radix anymore because the base is 2. Yeah. Okay, well, I think that's enough.
Yeah, I think that makes sense. All right, cool.
But yeah, now I'm worried like that 11100, right, isn't actually 4.5. Let me see if that's let me see if I'm right about that. 11100, right? So we have this, and we need to get it and figure out what it is, like not in 2s. Or we could just do this. We could just do this times 1, 0. This is all in binary. To the negative, I'm just going to use negatives instead of stupid stuff. This would be -1. So then we move it like this, right? And we get 1110.0, which this is 1, 2, 4, 8. Oh shoot. Oh wait, this is still in 2s. I forgot to change this from 2s. I forgot to change this from 2s.
I was like, wait.
This is negative. What is this in 2s?
5.
0, 0, 0, 0, 0 minus.
Yeah, it is -5.
1, 1, 1, 0, 0. We have a 1 here, and this becomes a 1. 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 Wait, does that work? So it's 0, 0, 0, 1, 1. Wait, but then this would be like, this is a 1, 0. Wait, no,
Wait,
no,
are we
I'm just
converting
so,
one
I'm being
one?
so stupid.
Are we converting 11100 from twos to binary? Is that what we're doing?
What I'm trying to do is converting it, yeah, from 11100 from twos to binary. I'm doing
Okay,
it
so then
really
wouldn't that
badly
just
right
be
now.
-4?
Yeah,
No,
it should be. It should
oh,
be.
wait.
It should be. It should be -4 if we did it right. But that's the problem. We did it right, right? This would
Wait,
be
no,
1,
that's not right.
0,
Hold on.
0, 0, 0. So this would be, yeah, so this is a 4's place. So this is -4. So the problem with that is that we have a -4, negative 0, 0, 1, 0, 0 times 10 to the -1. We shift that, and then we get -0, 0, 1, 0, which is -2, right? And that's not, wait, I must be doing something wrong here. Yeah, I feel like this is just completely off. Because the way that it should work, right, is that we are multiplying, but what we did to convert it is we split it up into -4 and 0.5. So we did -4 plus -0.5, and then equals -4.5, right? But then for some reason we decided that this, yeah,
Okay.
this is -2 to the 2.
I think what I'm gonna do is
-2 to the
search up
-1.
floating point representation on my own, because
yeah, that might be a good idea.
There's something
probably
we're
just
missing
confusing
here.
everyone.
No. So the problem is we're converting from twos to binary, but we're still using twos information. So I'm gonna look up how it's represented and converted, and then maybe
I think I did the conversions right actually. The problem.
No, I know it's confusing because we're still using information about the exponent from twos, and then we're wondering if like it's getting mixed up.
Yeah. So what I'm trying to figure out is when we
go.
Okay.
Right,
bye. Have a good time.
You did.
Shoot. Okay. Wait.
This stuff is like still so confusing to me.
Yeah, shoot. Okay, so I think what we did wrong is when we were trying to figure this out, we said -4 is the mantissa. Can that be right? Because the mantissa should be like -45 with an exponent of 2 to the -1.
I don't even know where to start with this. I have to like go over everything.
Hey, by the way, guys, the mantissa should be 9. In case you're wondering, -9.
Oh, you're right. You're right, because we're multiplying by 2.
Right.
Shoot.
Okay. Hey, you guys can carry on the conversation. I'm just worried if the Zoom recording might actually cut out in a
okay.
Because it's some kind of time recording. You can keep going. You can keep going if you want. I'll leave this on. I'll come back later, and if it's done, I will post it on YouTube.
Okay, well, there's like no one else here.
Yeah, everyone left already.
Shoot. So yeah, what we actually should be doing is saying that -9 times times 2 to the 1, no, -1 equals -4.5, right? And then we convert this into the mantissa. So this, we have 9 would be 8, no 4s, no 2s, a 1. Right, and that's in 5 bits. And then we need to convert this. So we would get 1, 0, 1, 1, 0, plus 1, so we get 1. Okay, so this is our 2s, so we would get 1, 0, 1, 1, 1, 1, 1, 1 for our actual answer. Yeah. Does that make sense? Because we added up here. We did like -4 plus 2 to the -1 instead of -4 times 2 to the -1. Okay, well, I have to go.
Hello, can you hear me?
Yep, yeah, we can hear you.
Sorry, my internet went out while you were talking.
Oh, okay. Yeah. Okay, so I think we should, I don't know, should I change the answer up there? Because we did it wrong, that's for sure.
If you're posting it, you should probably change
I'll
it.
change this before I post it. So that I don't put malinformation out there.
Yeah. People are gonna look over it and get like super confused.
No. Okay. So yeah, I will change this so that it makes more sense, and I'll rewrite it and like make sure that everyone understands that we did it wrong during the class. Okay, I'll go do that. Yeah, this is already going like 15 minutes over the class time, so I'll just do that on my own really quick, and then I can post it.
All right. Thank you so much for
No problem.
driving it.
Okay, I'm gonna stop sharing, and bye, I guess. Bye.
Bye. Have a good day.
Yeah.